Hello everyone, my name is Julia with Support Branch is Tutoring, and today we're going to be looking at an example, going over dynamics, looking at Newton's second law, forces, and motion. In particular, we're kind of looking at static and kinetic friction. So for this example, it says a little girl tries to move a suitcase across the room. The suitcase has a mass of 48 kilograms and a coefficient of static friction of 1.2. So for step one, almost always we are going to want to kind of draw a picture of what's going on. And so we have this suitcase on the floor, and we have this little girl that's trying to move the suitcase, right? And it doesn't say anything about angles, whether there's an angle between how she's pushing this. So we're going to assume that she's pushing it kind of in a horizontal fashion. And so I'm going to label here the force of the push here. And initially, this is not moving, and so we have no velocity and we have no acceleration because at first it's stationary and not moving. And what does the problem tell us? And so for 2, we're going to write out what we know. We know that the mass equals 48 kilograms, and that's the mass of the suitcase. And we know that the static coefficient of friction, which is this little weird looking mu, is 1.2. And so that's not a lot of information, but we can actually do a lot of calculations with just those numbers. So for these dynamics problems, the next step, kind of what's recommended, is to draw what's a free body diagram. And essentially you just use a dot to represent your object, and then we're going to draw out all the forces that are acting on this object. And so we need to set us a coordinate system here. I'm going to set a coordinate system as being positive up and positive to the right. And I'm going to have that she's pushing this suitcase to the right would be the force of the push here. And that is essentially what we're trying to find. That is our unknown. So what else do we know? What other forces are acting on this? Well, we always have the force of gravity. And as long as we're on a level surface, which we are, the force of gravity should be pointed straight down. And we know that the force of gravity always equals the mass to the gravitational constant. What else do we know? Well, we know that this suitcase is not moving up and down, right? So there has to be some type of force that's opposing gravity. We would call that the normal force. And it is basically the force of the floor that's pushing back up on this object and keeping it from falling down. So I'm going to put F in there. And then our problem tells us the static friction. So it doesn't tell us to say that friction is negligible. So we would assume we've got friction. And friction always opposes the motion. So if she's trying to move the object to the right, that means that our force of friction would be to the left because it's going to be opposite. And force of friction. Now, what do we know about friction? How do we calculate friction? Well, friction equals the coefficient of friction times the normal force. And for here, since we do not have any velocity 0, acceleration 0, we would use the static coefficient of friction versus kinetic would be if we were moving. And that's about it. We don't really have any other forces. So let's go through and kind of calculate some of these numbers. So I'm going to say step 4 here. We're going to calculate our forces. Okay, so we have, first of all, the force of gravity right here, right? And our force of gravity should equal our mass times the gravitational constant. So our mass, it gave us as 48 kilograms. And we know the gravitational constant is 9 meters second squared. Some people use 10 as an estimate and makes your calculations a little bit better, but we're going to do 9.8 for this today. So 48 times 9.8 is 470.4 newtons. Okay, so that is what our force of gravity is. Now, we have labeled that down is negative and the force of gravity is negative. So I'm going to put a negative here to denote that it's pushing down or pulling down. And what about the normal force, right? So normal force is up here. So we've got this equation. It's F net equals mass times acceleration. If you're going to remember an equation, this is one of the ones to remember because you're going to use it a lot. And we don't have any acceleration, so that means that this just equals 0. And the F net, what F net means is the sum of the forces, and we consider things that are 90 degrees apart as being independent. So here what we care about is the force of gravity and the normal force, because those are the only two forces that are acting in our vertical direction. So if we solve for the normal force here, we get F normal equals negative Fg, and if we substitute what we calculated for Fg, we're going to get a negative 470.4 newtons, which is positive 470.4 newtons. So again, as long as we don't have any acceleration in the vertical direction, we expect the normal force to be equal but opposite. And again, we're not at an incline or anything else that's making this more challenging. So those are equal and opposite. So why did we have to do all that work? Well, we need the normal force to be able to calculate our force of friction. And so let's go ahead and calculate the force of friction here. So the force of friction would equal to mu, the static coefficient of friction, which is 1.2, times our normal force. So 470.4, kind of 70.4, there we go, times 1.2, which gives me 564.5 newtons. Okay, and we have this going to the left, which is in the negative direction, so I'm going to put a negative there. So again, we're trying to find the force of the push here. We also know that F net, again, equals mass times acceleration, but this time we're talking about the horizontal direction. And we have no acceleration, so we know that that equals 0. And so that means that the push plus the force of friction has to equal 0. If we solve for the push, we're going to get the push is negative the force of friction. And again, we would have negative 564.5 newtons, which is positive 564.5 newtons. So the force that this little girl has to push on the suitcase to get it moving would be 564.5 newtons. Okay, so that is our answer for part A. The force that the girl has to push the suitcase to get it moving. So let's go ahead and jump to part B here. And for part B, it says after the girl starts moving the suitcase, if she pushes with the same force initially as in part A, what is the acceleration of the suitcase? So I'm going to kind of restart of like writing out what we know here. So what we know that the mass was 48 kilograms. We know that the coefficient of friction here, it gives us it as kinetic as being 1.0. So I'm going to put a K there to denote that that's kinetic. And then we know that the force of the push that we just calculated in the other example was 564.5 newtons. And everything else we have in terms of our free body diagram is going to look very similar. We still have the normal force, and the normal force should still be the same thing, 470.4. We have force of gravity, negative 470.4. Here we still have friction, and we have the force of the push. Okay, you might be looking at this going like, well, what's different here? Well, the difference is now the suitcase is moving. And so for our force of friction here, we still have the coefficient of friction, but we're going to use the kinetic value for moving times the normal force versus the static here. So the difference is that our mu has changed. And so if we kind of look at our F net equals MA, F net equals MA, again, if you're going to remember a formula, that's a good one. I'm going to say this is step 3. We're going to go ahead and calculate this. So we're looking for our acceleration, right? This is the value that we're trying to find as our acceleration. And we need to write in kind of what the sum of our forces is. So we've got mass times acceleration equals the sum of the forces in this direction. So we'd have the force of the push plus the force of friction. And from here, we just kind of need to plug in some of our numbers and solve. So we know that the mass is 48 kilograms. Acceleration, we don't know. The force of the push, we have as a positive 564.5. And we would have the force of friction here. We're going to need to put in a negative because it's in the negative direction. 1.0 for our mu times the normal force, which is 470.4. So if we solve for A, all we need to do is kind of divide by our 48 here. And we're going to get 564.5 minus 1 times 470.4. And then all of that divided by 48. So we get 1.96 meters per second squared. So we have an acceleration here equal to 1.96 meters per second squared. Okay, and that is essentially our answer for part B. It says, what is the acceleration? The acceleration is 1.96. So for part C, let me switch over to the next part C here. It says, after the suitcase is moving, what force would the girl have to push to keep the suitcase moving at a constant velocity? So we have the same scenario. Again, nothing's really changed in terms of our diagram. But now it's asking us a different question. So it's asking us, well, what if we don't want to have an acceleration? We want to have a constant velocity. Velocity, I'm going to put constant, and a constant velocity means that there is no acceleration. Then we still have F net equals mass times acceleration, but our acceleration here would be 0. And that has to equal the sum of the forces in the horizontal direction. So we would have the push plus kinetic friction. Okay, and our kinetic friction here would be very similar to what we had before. We've got the coefficient of kinetic friction times the normal force, and our normal force was 470.4. So we've got 1 times 470.4. Okay, so 1 times 470.4 would just be 470.4 newtons. And again, this is in the negative direction because it's pointing to the left. So I'm just going to solve for the force of the push here. We would get force of push would be a negative, the force of friction kinetic, which would equal negative 470.4, which would equal a positive 470.4 newtons. So as long as she is pushing with 470.4 newtons, you would expect that she'd be moving at a constant velocity, and the suitcase is no longer being accelerated. So if we look for part D here, part D says explain and compare the force needed to initially move the suitcase versus the force needed to keep the suitcase moving at a constant velocity, i.e. we're comparing our answers from A, C. So if you remember from A, we needed a force of 564.5 4 newtons to get this thing moving. And once it's moved, and that was with it would be kind of like no acceleration. That's to get it moving. Versus to keeping it moving at a constant velocity, we only need 474 newtons. And that's to keep it moving at a constant velocity. Okay, so we notice that our force needed to get it moving is larger than our force to keep it moving. The reason is because the coefficient of static friction is larger than the coefficient of kinetic friction, and that is always true. Okay, have you ever, if you've ever tried to move a box, it's always harder to get you have to push harder to get the box moving than once it's already moving, right? And so it's because of the fact that the coefficient of static friction is greater than the coefficient of kinetic friction. And it has to kind of do with the laws of inertia. The fact that an object in motion will like to stay in motion, or an object at rest likes to stay at rest. And so that's kind of the reason that we see that trend. So thank you for joining us as we kind of discuss some dynamics. I always like to encourage students to abide in Christ, right? Because we can learn physics. Some of us hate physics, some of us love physics, but physics isn't going to get you in heaven. Only Jesus will. So I'll leave you with this. Jesus replied, "Truly, I tell you, if you have faith as small as a mustard seed, you could say to this mountain, 'Move from here to there,' and it will move. Nothing will be impossible for you." Matthew 17:20-21. So we went through all this physics and calculating what the forces needed. But the ultimate force that we need for life is Jesus Christ. God bless. Jesus loves you.